Awesome. Thank you so much for the introduction. I'm thrilled to be here and to speak and discuss with you all today. So yeah, I'll kick things off and happy to answer some questions at the end, and I'll monitor the chat as well to see a pulse of where we're at and what people are interested in chatting about. Awesome. All right, so let me introduce myself really quickly here. As mentioned earlier, my name is Vincent. I'm one of the founding engineers here at Snorkel, and I lead our ML engineering team. Today, I'm going to talk about how we think about building AI applications here at Snorkel. Right? What are the principles behind how we approach AI engineering? Right? Where maybe the status quo is a lot more about staring at loss curves or getting stuck with, say, early assumptions around what your label schema is. Right? Maybe there's a big reliance on these end-to-end mega models, right, which go from inputs to outputs all at once. And I want to pull back the curtain a little bit and try to dig in on, hey, what are the pieces of traditional software engineering that we should be learning from and incorporating into our AI engineering practices? And what does a new paradigm, what does a new data-centric approach look like that actually anchors on principles like empirical evaluation, modularity, data-centric rather than model-centric development? I'll have a chance to talk through a case study and speak to these design principles and concepts that we use at Snorkel every day to build these sorts of applications. And I'm really excited to discuss with you all afterwards also how you think about this on your end and what some of your pipelines look like. So without further ado, I'd love to first share a little bit about how I started working on Snorkel and what sorts of problems I think about on a day-to-day basis. So I started working on Snorkel five plus years ago, back when we were still an academic project at the Stanford AI Lab. I was a core contributor to the open source project, if we have any early users out there. And since then, I've worked to build and deploy a number of these AI applications and systems supporting our customers as a lead of the ML engineering team. Our team is specifically focused on making sure that a lot of these concepts actually make it to production, and a lot of the value that is promised in AI is actually met with the types of customers that we work with. So I'm really excited to share a lot of those learnings with you today. So to get us started, I want to talk a little bit about how, hey, today practitioners are really interested in building these complex production-ready models that are actually much more advanced and complex than what you might see in benchmark or academic data sets, right? The scope of these models might include preprocessors, post-processors, business logic to actually tie to downstream KPIs. It's really, really important to be able to support this level of complexity to actually build useful models in production. And in a lot of these cases, right, what we found time and time again is that using black box, fully differentiable end-to-end models is actually a little bit of an insufficient approach, right? That's to say, when you use an end-to-end mega model, right, an end-to-end, big deep learning model for your approach, you don't actually get a lot of the engineering benefits that you might see in traditional software engineering approaches. Benefits like modularity, debuggability, introspection. These are principles that I really want to emphasize are actually critical to the development process and have a place in AI engineering today. So to talk through these, I'm going to start with a case study, a version of an application I've actually supported and seen deployed in some high value settings where the goal here is to build a social media monitoring application. This is an application that will help us talk through some of these design principles. So bear with me as I set some of the context here, and hopefully we can use this as the tool to understand in a very concrete way how we think about building these sorts of applications. So let's consider an application where we'd like to monitor company mentions on Twitter, right? So this is to say, hey, I want to see how people are talking about certain Fortune 500 companies, right? The sentiment of these Fortune 500 company mentions on Twitter. The input to the system might be a set of tweets or documents, text-based documents, and the output would be a set of, entities, right? Maybe the stock ticker symbol associated with each one of these companies, and an associated sentiment, right, for each of one of those stock ticker symbols. So again, the input is a set of tweets, and the output is a dictionary, right, mapping stock ticker symbols to a certain sentiment based on how that company was being talked about in production. Right. I'm sure the data scientists on the call are starting to spin about how you would actually, build a pipeline like this. It's an interesting one, of course. And, as a, a good ML practitioner, right, the first thing I'm going to do is, right, go to Twitter and see what the latest models look like, right, what the state-of-the-art fanciest models are out there. And I'm going to, try to throw in an end-to-end model, passing in documents as inputs and kind of, craft a loss function that helps me optimize this sort of sentiment and extraction problem all in one go. And I'm going to try to build this into my model all at once, right? Twitter's gonna point me to the latest paper, and I'm going to be off to the races, and it's going to be great. In reality, right, when I come to evaluate this system, let's say that, hey, my F1 score is actually not as great as I expect it to be. It's not as high quality as I would actually need to get this working, right, in production settings. What do I do next? I'll bring this problem to stand up, and turns out my teammates have a number of opinions, right? How do I actually understand where mistakes are coming from, right? Where are the issues in my pipeline actually coming from? And I sort of scratch my head and don't have a great answer for that, right? And maybe another teammate suggests, hey, I actually have some previous work, right, where I would created a dictionary of Fortune 500 companies in the past. Is that something I can actually take advantage of at all, or are errors coming from company mentions or sentiment predictions? A lot of the core problems that we see here is anchored in this idea that, hey, we have this end-to-end model, and it ends up actually being hard to understand fine-grained performance and to do this sort of error analysis, or to even use off-the-shelf resources that would be really helpful. And so the bit flip that I'd like to propose in this talk, right, the paradigm shift, if you may, is that practitioners need a new way of thinking about development workflows, right? Workflows that are much more practical and data-centric in terms of AI ML development. And we're not the only ones who think this, right? Sumit Chintala, the creator of PyTorch, made a similar observation earlier this year, right? This idea that in real world settings, right, deep learning is not enough, right? A single end-to-end model is not enough. And it's often a matter of actually decomposing this pipeline into reasonable modular subcomponents, where we see a lot of the benefits of traditional software engineering come in. So I'd love to use this as an anchor with this context, right, to start to talk a little bit about how we at Snorkel think about designing AI applications in a data-centric way. So let's jump into some of these design principles, and I'll go through a few of them here. Number one, down with the end-to-end model, right? Well, again, as I mentioned, there are certainly some problems where this is sufficient, right? Where it's fine to go end-to-end, and it's actually helpful to have one big loss function that captures the multiple objectives, or the end objective that you want to get running with. But often, right, our customers have found that this doesn't replace the engineering advantage of having a modular, composable system, right? A system where you can incorporate, custom models, multiple models at once, right? Pre-processing logic, business logic, like any piece of production infrastructure. It ends up being really important to take advantage of these, principles of modularity, and a single end-to-end black box approach often doesn't cut it, and doesn't give you the level of introspection that's necessary to kind of to ship high quality production systems. Second, right, while we want to de-emphasize end-to-end mega models, we do still believe in this idea of end-to-end evaluation. Right, it's really important that even if we end up decomposing our system in some way, we have a global view of the end objective, right, of what a practitioner or developer wants to do. It ends up being really important to understand, hey, what is the end outcome, right? What is the end-to-end application metric, that I can quantify and then tie to downstream business value? How do I actually think about that? It's actually really important to be able to, think and have this global view, and also iterate, right, at the end-to-end level. So evaluation and iteration ends up being really, really important, especially because to make these models useful, to make these applications useful, we want to be able to tie them to their downstream, business counterparts. Third, right, a little bit of an unintuitive one, right? This one is to say, hey, ML shouldn't be the universal default when you're building AI applications. In fact, in a lot of settings, a combination of expert systems, rules, heuristics, plus machine learning is a much more practical way to solve these types of problems, right? No matter no matter what Twitter tells us, it's equally important to assume that, hey, once we break down a problem, each component doesn't have to be a deep learning model, right? Each component, it makes sense to start with a sensible default, right? Often a heuristic that can then be swapped in based on a learned, ML component, right? Based on what we see empirically, right, in our error analysis. So the key takeaway I want from this slide is this idea that you can start with something simple, right? Start with software 1.0. You don't need to jump straight to software 2.0 style, ML-based approaches. These types of AI applications ends up being a great combination of the two, and this ends up being a very practical way to guide development, right? So you're not kind of jumping to the more complex approach right away. Lastly, I want to emphasize that, to build these sorts of applications in a data-centric way, programmatic labeling is going to play a really, really key role to flexibly adapting and developing the models in our approach, right? One, right, programmatic labeling is based on a heuristic-based approach to start. So hopefully you're starting to see this idea that, if you start with heuristics and use that as a way to empirically anchor development, it should be really easy to go from, say, a rule to extract, a company mentions in your document to a model that does this, right? And Snorkel's core programmatic labeling technology is a really great anchor point to building on top of that modularity, right? Another thing I want to mention is these days there's a lot of excitement around pre-trained models and self-training and these sorts of problems that are have become really, really effective in a lot of settings, right? Where you're training on a very general purpose distribution or problem setting, and you can actually leverage a lot of those weights or embeddings for a specific problems. The issue is that there is this last mile, right? There's this last mile where you need to be able to fine tune the models to your specific data distribution, to your specific problem setting. And this is where being able to move really quickly with an approach like Snorkel, right, where you're able to build training data sets really quickly via programmatic labeling and deploy these models and iterate, right, using the Snorkel flow approach, ends up being a really critical part for how we think about AI application building. I won't focus too much on this Snorkel development loop in this particular talk, but my colleague PK is going to be giving a separate talk later on about the merits of weak supervision and programmatic labeling. So I encourage you to check that out as a follow-up. But to recap, right, these four design principles are ones I want to keep in the back of our minds as we go a little bit more into the details of, hey, how these can be operationalized in your actual AI engineering practices. So to move forward here, right, I want to cover a few practical key concepts that we found are really helpful when building AI applications. So going to go with a few definitions to help us build some shared vocabulary and context. First, I want to introduce this idea of an operator, right? This idea that, hey, we have this core primitive, right, and an operator, which is simply put, just a transformation over one or more data frames, right, in your data set. You can actually think of a classifier as an operator that maybe adds a prediction column, right? And in this case, maybe we're trying to classify emails, with subjects and bodies. The classifier operator has the job of just adding a column, which is a prediction, right, about whether this particular row in our data frame is spam or not spam. One key thing I want to point out is that operators should be modular, right? Operators can be heuristic, as I mentioned, right? You could say something like, hey, if someone mentions free money in the subject of your email, let's label that spam, right? That's a very reasonable way to go about building a system like this, and it might actually solve a problem in a lot of ways, right? This is what I'd been alluding to when I was saying, hey, start with something heuristic, right? Start with something simple and see how that does before jumping straight to the ML solution. Of course, once you've explored the heuristic option, the idea that a modular an operator is modular lends itself to replacing that heuristic or building on top of that heuristic to actually train a model, right? What we call a learned operator. Leveraging some state-of-the-art or off-the-shelf model libraries like sklearn or Hugging Face. It should be really, really easy to swap in a heuristic or rule with a model that generalizes right beyond the scope of a more heuristic approach. So modularity is the key that this slide is trying to get across. Next, I want to introduce this notion of an application, right? I've talked about so far how we think about individual transformations to data frames, but in reality, right, the systems that are actually useful to build end up being these end-to-end applications that serve downstream business and product needs, right? Formally, right, in Snorkel, we implement these as DAGs or directed acyclic graphs over operators, right? So operators will have edges between them to indicate data flow. And end-to-end applications are actually composed of maybe one or more models and the associated preprocessors and business logic to get the data in a format that actually makes sense, right, for production use cases. As you can imagine, right, each one of these applications can also be templatized, right, in what we call application templates. So how you think about information extraction from unstructured text is going to look very different from how you think about information extraction or entity linking over say PDF documents or other types of modalities, right? These sorts of templates end up being really, really helpful to guide our customers along in thinking about end-to-end applications, which again, formally, right, for the developers on the call, can be defined as a DAG of transformations over each one of these individual operators. Awesome. Another concept I want to push forward here is this idea that, hey, in your DAG of operators, it should be really easy to diagnose quality at a local and global level. This is tied to a point I made earlier around, not only do you want to be able to see end-to-end scores, you want to be able to see component-wise performance of each one of your each one of the pieces in your problem, right? This is a very an uncontroversial idea in traditional software engineering, this idea that we should be unit testing, right, and kind of understanding component-wise decompositions of the broader problem. The same sort of system should apply here, right? We should be effectively unit testing individual pieces of the workflow and making sure that we understand quality at both a local, right, unit test, and also global, right, integration test level. And so with these ideas in mind, let's revisit our social media monitoring application and talk about how would we actually build something like this, right? Using these key concepts and design principles. So again, the goal here is to go from tweets to stock ticker symbols, to dictionaries of stock ticker symbols, to sentiment classifications. Let's say that the first thing we do is actually start with a template, right? This is a tried and true approach, maybe for this particular problem type. We're going to start with a template that decomposes the problem rather than assuming we're going to start with something end to end. We're going to actually assume that there are multiple subpieces to this problem, right? That help us break this into a best practice in the industry, right? In Snorkel Flow also, right? These are initialized all at once with very sensible defaults, right, to kind of get you up and running in a very, very quick way. And so I'm going to now go through each one of these components to explain, what their roles are in this system and how we can actually think about development over each of these subcomponents. So let's start with the entity tagger operator, right? The goal of this entity tagger at the beginning of the pipeline is to extract company mentions from our tweets. And we can start with something heuristic, right? Maybe something that takes advantage of organizational resources. Let's assume that, hey, it's not unreasonable to think that our teammate actually had a list of, Fortune 500 companies, a dictionary of this with aliases that they scraped earlier this quarter. Let's take advantage of that, right? The reason I give this example is because once we decompose the problem in this way, we're able to actually, pull in heuristics and resources and more traditional software 1.0 approaches into an application and leverage that as a first pass, right, to get us going and help us move quickly in building this application. Second, right, we're going to assume that we have each one of these company mentions already extracted from our documents. We want to actually classify the sentiment of each one of these mentions, right? And you can imagine using the context around each one of the, extracted company mentions, extracted Fortune 500 companies, and using that context, right, the surrounding words or tokens to make a prediction about how people are talking about it in a particular tweet. So this is something we can be building, with an sklearn model, a very simple, bag of words approach. Something we can certainly build in using a learned model, right, in this case to make this sort of classification. Next, right, the linker's job, right, the entity linker's job is to actually say, hey, we have multiple mentions of companies in this particular tweet, but different mentions might actually be referring to the same company, right? The different mentions might be referring to the same entity under the hood. So we want to have an entity linker that has the job of mapping each one of those surface forms, right, to a normalized entity, right? In this case, we're going to say, hey, for example, Nokia might show up in different formats in our document, but there's only one stock ticker symbol that we're going to map each one of those to. And again, this could be done in a heuristic way, right, using something like a fuzzy matching approach, right? It just fuzzy matching over number of character overlaps, for example, as a very coarse-grained way to map and disambiguate each one of these entities into a canonical form. Next, I want to talk about this reducer operator, which has the job, it's a little bit more of a trivial operator, but it has the job of simply heuristically aggregating each one of these mention level predictions into entity level predictions. So again, it's basically doing a group by over the linked entity and saying, hey, for all the predictions for mentions over Nokia, I want to just aggregate these and figure out, okay, what is the overall sentiment for Nokia in this document, right? This is, a little bit nuanced, but I mentioned it because this nuance is real, right? In the types of practical applications that need to be deployed to production. So it ends up being helpful to explicitly call out that, hey, this is a step that's actually helpful in these settings where you're first, breaking down the problem at a mention level and then aggregating those predictions to the entity level. So let's assume that we have a first pass at this pipeline in, right, where we have some components that are heuristics, one component, the sentiment classifier, that is maybe a model to start with. Where do we focus our attention next, right? This is where something like local operator scores come into play, right? This is where actually having a good sense of the component-wise evaluation of our system is actually really, really helpful. And so we're able to dig a little deeper and say, hey, a lot of the parts of this pipeline are actually doing a pretty good job, but end-to-end and for my entity tagger, actually, I'm not performing at the quality that I'd want. So this is a really great way to help prioritize development effort, right? If you have access to these local scores at each step in your pipeline, you're able to double click and go a little deeper to debug what's going on. This is what I mean by development should be driven by empirical understandings of the pipeline, right? Rather than again staring at loss curves or just making guesses at hyperparameters. This ends up being a much more systematic and concrete approach to building these sorts of end-to-end applications. And so what do we do next? Let's focus on the entity tagger. Let's try to improve it. And so, right, recall that earlier we had used a heuristic, right? We'd used our teammates' dictionary to build an entity tagger, and in this case, we might want to pull in one of the latest and greatest, Hugging Face transformers to help us with the company extraction process, right? We'll use Snorkel to create a training data set really quickly and iterate over the quality of this particular model, and ultimately, right, the goal would be to deploy an application that is actually high quality, right? That improves the quality of the entity tagger, because now instead of using a heuristic, we're learning, right, and generalizing beyond the scope of that dictionary, and we're kind of slotting in place, right, because the system is modular. We're slotting in place a machine learning model to do the job of what the dictionary was doing, right? So what I just showed was, again, a very high level here, but the idea I'm trying to get across is this idea that, hey, we decompose the problem, right? We're able to quickly get started with a sense of very sensible defaults, right? Within an afternoon of development, we're able to quickly spin up an end-to-end pipeline just to see where we're at, right? Just to get something up and running that maps to our end problem. And then we were able to pull back the curtain and understand, hey, where are we actually making mistakes in our pipeline? Where should we be focusing effort? So improving one piece of our pipeline, in this case, the entity tagger, ends up potentially improving our end-to-end global score. And so this is the type of modularity and decomposition that ends up being very practical for development purposes, and is something that a lot of our customers have really anchored on. Again, right, you can imagine all this certainly can be done with an end-to-end approach, right? All that is possible in Snorkel, but for a lot of these production level systems, we're finding that decomposition is really important, and that isn't a surprise, right, for folks coming from traditional software engineering backgrounds. So a few summary points for what we've covered here, right? One, we were able to decompose a complex application, right, where we weren't just doing like a document level classification or something. We were trying to do an extraction and classification and linking problem all in one. We decomposed that into a set of components that could be easily understood. Once we had those components, we were able to diagnose quality and understand where in the pipeline we need to prioritize development effort. So again, much less guesswork around just hoping that the loss goes down in an end-to-end way. You could actually just focus effort, right, and say, hey, great that I started with a heuristic. Great that I now know, right, that this was the part of my pipeline that was struggling. I can just replace it with something that works a little better. I can write some labeling functions and quickly spin up a training data set to replace to train a model and replace that heuristic component and improve end-to-end performance. And as I mentioned, right, iterating on each of these subcomponents needs to be fast, right? It needs to be flexible and adaptable. And that's where Snorkel's programmatic labeling workflows come into play, right? That's where writing labeling functions, quickly being able to train models and iterating on that quality as a sort of inner loop, right, for this application development process ends up being a really critical approach to speed up development processes here. So overall, right, of course, this sort of iterative development is made possible, right, in Snorkel Flow, and it's something that we've actively learned from being in the field with our customers and have baked into the systems that we're building today to make AI application development, AI engineering, much more practical for the types of complex problems that we're seeing in production settings. So with that, I will pause and open things up to questions. But yeah, thank you for listening to this talk, and I'm happy to engage via questions now. let's see. I will check the chat. I guess if people want to unmute, that's okay too. But yeah, I'll just leave the space open in case anyone has any questions. But yeah, I'll be around. You know, my contact should be shared, and I'm very happy to continue riffing on any sorts of real world application that that folks out there are building.